Hi students, this is Mr. Yang. Today we are going to talk about 6.4, where we will learn about the segments in circles. So previously we have learned about angles in the circles. This time we're going to focus on segments that's generated by some secant lines, chords, or tangent lines in the circle. Prior knowledge, we are going to quickly go over some factoring questions. For question A, x squared, if it's already an x squared, there's no a in front of the x squared. We can just set it up as x inside each parentheses, and then we are trying to find the number pairs that can add up to -10 and multiply to get a 24. And that would be a -6 and a -4. There is the factoring for A. For B, we do have a number in the front and a number on the back, so this time we can't do x and x. We gotta use the cross method. If you forgot about these, you can go back to Unit 1 and refer to that. So multiply the A and C, and that's going to give us a -72. And this is a 1x, and put that 1 on the bottom of the cross. Then we make fractions. The combination that we need to multiply again and get a -72 and adds up to a +1 would be a 9 and a -8. And then let's not forget to include the leading coefficient. So 6x and 6x. That can be simplified to be 3x over -4, and that could be simplified to be 2x over 3. Factoring 2x plus 3 and 3x minus 4. And that is B. C. These are both perfect squares, so we can just go right to the difference of perfect squares. 2x plus 9 and 2x minus 9 equals 0. And then we set each one to 0. And then we can solve to get the answer x equals -9 over 2 and x equals a +9 over 2. And that is C. Moving on, the first theorem we're going to talk about for segments of chords theorem. If two chords intersect in the interior of a circle, then the product of the length of the segments of one chord is equal to the product of the length of the segments of the other chord. Well, that's a lot of word of. So let's see what it means. It actually means, for example, we have AB, that's a chord, and CD is another chord. Because they're intersecting at point E, AB is being cut into two parts, EA and EB. CD is also being cut into two parts, EC and ED. It's basically saying for each of the chord, the two parts multiplied is going to equal to the other one. So here it is. EA times EB is the same as EC times ED. As for the proof, we can connect AC and BD. Now, if you didn't notice, this angle CAB is facing this arc BC. This arc BC is also being faced by the angle CDB. So they are both inscribed angles and they are the same. And we can do the same thing for the other side. This arc AD is being faced by angle ACD and is also being faced by this angle ABD. And at these two triangles, they also have the vertical angles right here. That's why these two triangles are similar. Use AAA angle to prove that triangle AEC and triangle DEB are similar. And then we can actually set up the ratio EA compared to ED is the same of EC compared to EB. And if we actually simplify that, that is going to give us EA times EB equals EC times ED. That's the first one. Let's use that to solve some questions. Question 1. Solve for x. Two segments multiply together. So for this one is the 9 and the x, so 9x equals, for the other one is the 6 and the x plus 2 equals 6 times x plus 2. Now we need to distribute. 9x equals 6x plus 12. Subtract x on both sides. 3x equals 12. So x equals 4. Next, example 2. X and x plus 4 is on the same one. So x times x plus 4 is the same as x plus 2 and x plus 1 on the other one. X plus 2 times x plus 1. Now we need to distribute to simplify. So x squared plus 4x on the left side. Right side, remember to do your distribution. That's going to end up giving you x squared plus 3x plus 2. Then the x squared cancel. We are left with 4x equals 3x plus 2. Subtract 3x on both sides, you will get x equals 2. But we're not done. The question is not just asking for x, it is asking for ML. ML is x plus 2 and x plus 1. So together, that is 2x plus 3, and plug in the 2, it's got to be 2 times 2 plus 3, which is a 7. JK. And I forgot to mention, by the way, in your notes I did have a typo, so make sure you change it into ML. It's not MJ. So here, JK is going to be the x and the x plus 4. That's together 2x plus 4. Plug in the 2. 2 times 2 plus 4. So JK is going to be an 8. That is example 2. Moving on. So for a circle, the previous theorem have 2 chords. Now, if we have some secant line and tangent line, we may have some other theorems. So to introduce that, we do need to understand if we have a secant line that's touching the circle or going through the circle twice, this little part outside is going to be called the external segment. And the whole thing, because it's a secant, but it's not a line that's going all the way through it, just stopping on the circle, that is going to be called a secant segment. Then the other one is the tangent segment, which we have seen before. So here's the segments of secants theorem. If 2 secant segments share the same endpoints outside the circle, in this case right here, same endpoint, then the product of the length of one secant segment and its external segment equals the product of the length of the other secant segment and its external segment. So here's what it means. EA times EB equals EC times ED. Something to be careful with. It's not just 2 parts. It's not just this part times that part. It is not. It is, in fact, the external part times the whole thing. The external part times the whole thing. That's kind of the difference between this and the previous one. The previous one, you just separate the segments. There's nothing to be multiplied with the whole thing, the whole chord. But here, when you have a point outside the circle, you do need to do external part times the whole thing. Now let's look at some examples. The outside part is x plus 3. And the whole thing is going to be x plus 3 plus 13 is x plus 16. That is going to equal to the other one, x plus 2 is at the external part, and then is the x plus 2 plus 17, which is x plus 19. Now we do need to actually do our distribution to simplify that. So here it is. X squared, left side, plus 3x and 16x plus 19x plus 48. Is going to equal to x squared plus 21x plus 38. The x squared would cancel, and you can subtract 19x on both sides and then subtract 38 on both sides. That's going to give you 10 equals 2x, so x equals 5. You can always put it back in to check. When x equals 5, this part will be an 8, and the whole thing will be a 21, multiplied to be 168. 5 plus 2, this part is 7. The whole thing is 24. 7 times 24 is 168. So they actually do equal. That's example 3. Example 4. Outside external segment times the whole thing. So 3 is the external segment. The whole thing is 3 plus x plus 2, which is x plus 5. For the other one, external part is x plus 1. The whole thing is x plus 1 plus x minus 1, which is 2x. Now distribute 3x plus 15 equals 2. X times the 2x is 2x squared. 1 times the 2x is a plus 2x. I can now set one side to a 0 so I can solve the quadratic. 2x squared. Subtract 3x over, so minus x. Then subtract 15 over. You can choose to use the quadratic formula, or you can try to factor it. In this case, on the top, 2 times negative 15 is negative 30. On the bottom is a negative 1. 2 numbers that multiply to get negative 30 and adds up to a negative 1 would be a negative 6 and 5. Then let's not forget to put 2x on the top of the fraction. That's going to give you x over negative 3. So it could be factored into x minus 3 times 2x plus 5 equals 0. That's going to give you x equals 3 and x equals negative 5 over 2. However, we are talking about length here. So we can't have the negative number. X equals 3 would be the answer for example 4. Now moving on, the last type. segments of secant and tangent theorem. So the basic idea is, for example, if we go back and look at the previous part, you can choose to push this line out even more, so it kind of become a tangent. Then basically that means the external part of the whole thing are the same thing, so you just do the tangent segments times the tangent segment itself, which is exactly what the third theorem is. You see, EC times the whole thing ED is equal to EA squared, the tangent segments times itself. If a secant segment and the tangent segment share an endpoint outside the circle, then the product of the length of the secant segment and its external segment equals the square of the length of the tangent segment. And of course, we can also prove this. We can connect AC and, well, there's no BD in this case. Actually connect AC and AD. And it's kind of a very similar idea. This angle is facing this arc. But this arc is also in the tangent line and this chord. So that means this angle is going to be half of the arc as well. This inscribed angle is half the arc. That angle is also half the arc. Of course, they are the same. And that's the first thing. Second thing, they do share this angle right here. If they share two angles already, for sure they share the third angle. So angle, 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 again, these two triangles are similar. We can use that to separate the ratio. Then we would get EA squared equals EC times ED. Now example 5. The tangent segment is x, so that's being squared, is equal to external is 1. The whole thing is 1 plus 3, which is 4. So x squared equals 4. X would be a 2. That's example 5. Example 6. 16 is the tangent segment is equal to the external segment, which is x, times the whole thing is x plus 8. So we would have x squared plus 8x minus 256 equal 0. Now for this one, you can try to factor, but the factor is you can't factor. You can't find two numbers that adds up to an 8 and multiply to get negative 256 just by factoring. You can't find them. So let's actually use quadratic formula. X equals negative b is negative 8 plus or minus b squared is 64 minus 4 times 1 times negative 256. All over 2a, which is 2. Keep going. Negative 8 plus minus 64 plus 1024. And the whole thing is putting over a 2. Keep going. Negative 8 plus minus. That is 1088. And that could be simplified to be 8 square root of 17 over 2. And since x is positive, there's no way you can use a negative number, subtract another number, and get a positive. So we are going to ignore the negative sign now. So x is going to have to be negative 8 plus the 8 square root of 17 over 2, which simplifies to be negative 4 plus, there's no minus, plus 4 square root of 17. And that is also just RS. That's example 6. And that concludes everything for 6.4. Thank you.